Hello, class. I'm going to record a lecture here. No video this time, just a whiteboard. And I'm going to go through the equations of motion and how we derive those. They're derived in the textbook in this class using just algebra. We're not going to use calculus. So it's kind of, like I said, kind of waving our hands. It's not traditionally how it's done, but it'll serve our purposes for what we need it for. And you don't really need to derive the equations to solve the problems and different problems in physics in motion like this. But I'm going to go through it because it's good to know, and I'm sure some of you are curious. I'm going to follow the derivation in the book, which is chapter 2, section 5. So for these equations of motion, we're going to assume that acceleration is constant. And so this bar over the A, or any number, means a mean or average. So that's the average acceleration. We're just going to call that A, and that's going to be constant. Many times that'll be gravity, but it can be any other thing. But that's an assumption that all these equations of motion are based on as a constant acceleration. So for the first equation, we're going to derive one for position as a linear equation in time. So we're going to start with our average velocity, which is v here. And so as we learned before, the average velocity is delta t, or delta x over delta t. So this is the change in position over the change in time. We can see that on our position versus time graph over here. So this is the difference in position. This is the x-axis. This is it changing. And this is the difference in time. So those are delta right there. And we know that the delta x is going to equal the final position minus the initial position. So that's xf here. And I can't write subscripts, so it would normally be x sub f in your textbook, but it really doesn't matter. It saved me some time. So xf here is the final position, and x0 is the initial position. So the difference between those two, xf minus x0, is going to be delta x, and that's what I have on the top of the equation here. Then on the bottom, I have the final time, tf, minus the initial time, t0, and so that's tf minus t0, and so that's delta x over delta t. And I'll actually take these here. Move this delta over here. That's going to be delta x. This is delta t. I'll just get rid of that. So we already have that there. That's delta t. Right there. All right, so our equation at this point. So if we make our final position just a variable, so it varies along this line, as you can see, then x is just going to be x. The final position is going to be variable of time, the position as a function of time. So as you can see here, the position changes as we go in time, and so that'll be the function. So if you can imagine, this line here is where we are, position, and that's where we are in time. So here at our initial time, we're at our initial position. Final time, we're at our final position. And you can imagine this being like a bead or something like that here. So that would be where we are. And so the final time is going to be variable too. So that's going to go to t. That's going to be our variable. And our initial time, we can always make equal to 0. And that's equivalent to starting a clock at 0. And so there are times where we could start at a time we'd start the clock and then start the motion at some time after we started it. But it doesn't really make sense, and we don't need to do that. So we can always go to time. Initial time equals 0. And that's equivalent to moving this axis. So we can always just move this axis here. You can make t0 equal to 0. So that's just going to be 0. right there. We still have our T initial and T final. So we're going to make that. This is our function of x is a function of t minus initial position is going to be our delta t. And so this is going to be our variable here. So delta t is going to be t minus 0. And that's what we have here. We go down to this function here. So this is x is a function of t. That's there. That's where our particle is. And move this down here. So this is the equation we're going to start off with. And all we do is some algebra at this point, and that's how we'll get a linear equation for position. This is going to be the average velocity. And actually these are it's going to be the average velocity throughout. So I should make these averages. That's going to be the average velocity. Okay, so this star is a multiplication, and we take the t from the denominator and move it to the other side of the equation. And that's what we have here. And then we move the x0, the initial position, to the other side. And when we switch it, each side of the equation, and this is going to be our first equation. And this is an equation that you'll use quite a bit. And it's a very common equation, and it should be fairly intuitive. Basically, it says that our position as a function of time is going to be our time times the average velocity that we're moving is going to be the distance that we cover. And then we just add that to the initial position, as in here. And you could also make the initial position go to 0. I forgot to cross this out. So that goes to 0 there. And we could actually make that go to 0. All you would need to do is move this x-axis to this point. And so there, we would make that equal to 0. And then that could actually go to 0. And we would just have x as a function of t equals v, average v times t. And we'll make that the average. And so that's our first equation. Thank you very much. I'll cover the rest of them in subsequent lectures. Thank you.